Hello everyone. This is Astarag and we are going to discuss about reinforcement learning for language models, and we'll be discussing about GRPO or group relative policy optimization, which was introduced by DeepSeek in their post-training pipeline. Before jumping into GRPO, let's first discuss about traditional reinforcement learning. In traditional reinforcement learning, you have an agent which is responsible to take an action, and this action goes to an environment, and the environment is responsible to sample the next state and also give reward to the action. And this next state goes into the agent again, and this loop continues till we reach the episode end. For language models, there are few changes. Here, the agent is the language model, and the action is the whole completion by the language model. And here, the environment plays as there is no multi-turn, or we don't have to send the next state to the language model. The environment plays a role of giving rewards to the completion, and also it samples the next data point or batch to the language model to be generated to generate action. So if we see it in a tabular form, the traditional RL setup has a state, and in language models we have the prompt to the model as the state. The action is the whole completion, or we call it as bandit problem because it's just one considered as one action. And the reward is the format or the accuracy rewards. The format is the desirable format that you're expecting the language model to respond in, and accuracy is the ground truth response or any rubrics you have to judge the answer. Agent is the language model, and the environment plays a role of either giving out rewards or it can be a tool calling endpoint. Let's discuss this tool calling endpoint in detail. Here, I'm just repeating the traditional RL setup. You have a language model, it takes an action. Either it can do a tool call where it can say something like it can call a Python interpreter or an API, and the environment will be responsible to get the tool outputs and pass it in the next turn to language model. Or the model can choose to end the conversation, which is the rollout end, and in that case the environment will get me the reward for all my completions, and it will sample the next prompt that will be given to an LLM. So the environment plays a role of giving out rewards, doing tool calling, and all those things. So now let's discuss about action in reinforcement learning for language models. As we discussed here, the action is the whole completion. So how are we going to, but the response from the language model is going to be set of tokens. So how are we going to merge into a whole completion? So for that, so let's go through the transformer backbone. In a transformer backbone, we have a beginning of sentence token. It goes through the transformer layers, then it outputs logits, which is of the shape of vocab size, which gives probability for each of the tokens in our vocab size, and the normalization of logits happen through this log softmax. And then we gather the indices for hello from our vocabulary, and we find how much likelihood, how much probability did our model assign. Here it's the raw logits that I'm showing here, but you will get how much probability that the model assigned to one of the completion. And similarly now, as it is an auto-regressive transformer, now beginning of sentence and hello go to the transformer layers. Then we again generate the logits, and we generate the log softmax, and we gather how much likelihood did our language model assign to the word world. And so these are like set of tokens. Now to combine this set of tokens into one action space, what we do is we take the sum of this log p token, and um, and the sum of all the probabilities of each of this token is called as log probs. And when you take a sum, we are basically talking about the likelihood of the entire response. And now you have compressed the action space into just one number for a um, for a sequence. Here, like we come, this was the log likelihood of hello, and this was the log likelihood of world, and we have combined into one scalar value. So now we have compressed the action space into just one scalar value, and this is going to be very key in when we're optimizing with reinforcement learning. Now let's see in traditional RL setup how this plays out. So you have the agent and you take the action, and this action, as I said, is set of tokens S1 till Sn, and Si is the ith token. And and now the whole completion action space is the log of the probability of the first token, second token, third token, and so on. And when we combine it, we say it's the action for the entire completion, and that is what goes in as the action for reinforcement learning for language models. So yeah, after we combine it, and in supervised fine tuning, we optimize for this log of the sequence, uh, which is the combination of this log probs. But in reinforcement learning or reinforce, we we weight the log probs, the sum of the log probs, by the reward given by the action. And in supervised fine tuning, we have the gold generated data set. So every token is, we should maximize the log likelihood of every token. But in reinforcement learning, every next token is maximized based on the how much reward they give us. So reinforcement learning is basically a reward weighted supervised fine tuning, and this reward is given by the environment or a reward model or any or it can be a verifiable reward, like if you're doing code completions, it can be how many test cases, or in math if you have the ground truth. So so the main takeaway is the reinforce is basically the reward weighted supervised fine tuning loss. And let's formalize with the math formula. In the reinforced loss function is given by the reward, the episode return, which is the whole response, and is the sum of the action of the log probabilities that we saw earlier. Now, another important concept in reinforcement learning is bias versus variance. So, if you're sampling small number of responses or one response, then your model will be really good at estimating those responses. So you will have low bias for them, or you will be unbiased. But uh, one rollout or handful of rollout is very noisy, and it can lead to high variance, and it can lead to unstable training. But there is a trade-off. If you increase the number of rollouts, now you are able to reduce the variance, but now uh, your your weightage for each of those trajectory would reduce, and you might have higher bias. And the trick for correcting for that is called as importance sampling, and we'll be discussing this in depth later. But yeah, so the main takeaway is more samples you have, you would have lower variance as you are estimating many trajectories, and you would have higher bias because now each of those trajectories get less weightage. And the fewer the samples, now you would have lower bias, as you will be good at estimating those trajectories that are in a batch size, but you would have higher variance because you are not seeing a lot of responses, a lot of actions, trajectories. So this, to mitigate this bias versus variance trade-off, in reinforce we generally subtract a baseline from your reward. So as we have seen this earlier, this is the log, sum of the log of the probabilities, and we multiplied with the reward. But now in addition to the reward, you'll also provide a baseline. So what is this baseline? In reinforcement style algorithms, the baseline is the average reward of all the trajectories for the prompt. So you take a prompt, let's say you generate 8 responses from it, and if the baseline for those 8 responses would be like you take the sum of the rewards and divide it by 8, which is the number of responses. So the mean of those rewards is your baseline. And advantage is basically advantage of a trajectory is basically how good is this trajectory as compared to the average. So when you subtract the reward of a trajectory from the average, so you are kind of signaling how good is this trajectory as compared to the baseline or the average. And many people have found different versions of the baseline. One of the version is called as RLO, reinforce leave one out. Here in the baseline, we take the average of all the trajectories, but when you are calculating the advantage of a particular trajectory, you do not take that trajectory for the average. So it is like you leave out the current trajectory from the reward, in turn making it unbiased, and you just take the advantage by calculating the baseline. So hence you say this j is not equal to I when you are calculating the baseline for one of the trajectory. And one thing I would like to say that by trajectory I mean responses, and in RL for LLMs, as I said, the whole response is called as action, and I'm calling that to be trajectory. So trajectory, response, action are all same. I'm using them interchangeably. Okay, now let's get into the GRPO, or Group Relative Policy Optimization, introduced by DeepSeek. This is the objective function for GRPO, and we will be going over some of the key ingredients in this objective function: the normalization, the policy ratio, clipping, advantages, and beta is basically a hyperparameter, and we'll be discussing at the end about KL divergence. Let's get started with advantages. So as discussed earlier, in RL for LLMs, you have a prompt, you generate multiple responses, and we sum the log probs of each of those tokens to get the action space, and we get a reward. So let's go through some of the notations here. So let's say for prompt 1, you generate this action, and you generate another action, and then you sum of the log probs and you get the reward. And the notation for S111 is here. It means you belong to group I or group 1 or 2, sequence J. Here we have two sequences, so sequence 1 and 2, and token K. So you are incrementing the token count here. So this completion has n tokens, this completion has m tokens, this completion has k tokens, and this one has p tokens. And these are the rewards for each of those completions. And the sum of the log probs is basically the action space. Now, as discussed in reinforce, the advantage of completion, or the completion 1, which is the group 1, the first completion, is basically its reward plus minus the mean of the rewards for that group and divided by the standard deviation in the reward. So the advantage that DeepSeek used is the reward minus the mean divided by the standard deviation. So this is the advantage of completion. This is little different than how the reinforced advantage was calculated. There we only had R1 and the mean, but here we are also considering the standard deviation. That's the only change as compared to the reinforce. Now, if we go through the same exercise for another sequence for this prompt 2, so you have these log prompts, and the advantage of this is the reward minus the reward of the average of this group. So that means this sequence and this sequence, and the standard deviation of this sequence and this sequence. So now if we fill in the advantage for all of these completions, you will get A11, A12, A21 and A22. So in your batch you have two prompts, two completions per prompt, and you have calculated the advantage of each of those prompts. And now now let's define another notation, C11, which is the completions for the first sequence. So this one, first sequence of group 1 or prompt 1, and this is basically the summation of all the tokens, and we normalize it by the length of the sequence. Here it is n, so we normalize by the length of that sequence, and we calculate this for all the sequences for brevity and in symbols. I'm not showing for others, but yeah, you basically calculate for all the sequences, and as you have two completions, so you normalize by the two completions, you take the advantage of all the tokens for a prompt, and you take the advantage of all the tokens for the other prompt, and then you can add them through this combination where you normalize by the number of groups and you have number of completions and you weight them with the advantage, and this is your action space, which is basically sum of these log props. So this is your GRPO objective, and I would really suggest you to go through the calculations, go through the notations again to get a sense of it, and kind of understand how things stack up as compared to reinforce, and the only change that you can see is not having the standard deviation in the advantage calculation. And so we discussed in detail about the GRPO loss. Okay, let's discuss some of the problems with our advantage calculation and the normalization that we did for GRPO. So the problem one is this is our prompt, and we had two completions from our prompt with multiple tokens, and we calculated the advantage by taking the reward, subtracting the mean, and then dividing by the standard deviation. And generally this standard deviation is also comes with an epsilon, like we add a small factor like 1 to the power minus 8, 1e to the power minus 8, because standard deviation can also go to 0, which is the main theme of this slide. So let's say you have, for this prompt, you have easy or very hard problems. When the problem is easy, all your completions are going to get it, and your reward will be, all of them will be 1, or the max reward that you can achieve. And on the alternate, if all the problems are hard problems, all of your reward will be the mean reward, and this leads to the standard deviation being 0. And if your standard deviation is 0, and because of epsilon you have a very small term in the denominator, and this can artificially inflate the advantages for very easy and or very hard problems. And so your model will even if it's a easy problem, the model will get a lot of gradients because the advantage is artificially high. Or if it is also a very hard problem, the model will get a lot of gradients for those tokens, and even if the model couldn't solve the question. And this can also pollute the gradients for the rest of the sequences in your batch, which have not a reward between min to max. So the standard deviation is kind of a problem, and also we didn't see this in the reinforce loss. If I go back uh, to uh, the baseline only has the mean of the rewards, and also RLOO objective has the mean of the rewards except the current trajectory. So this standard deviation was introduced by DeepSeek, and in subsequent papers they found that this standard deviation to be problematic. Now let's see how people solved this standard deviation problem. In the Dr. GRPO paper, or Dunn Wright GRPO paper, they completely removed the standard deviation. And in DAPO paper by ByteDance, they would filter out the prompts which have standard deviation nearly equal to 0, so that they are not learning from those things. So they are filtering out the easy and the hard problems. So So another problem that we saw uh, from our normalization is we took the log props, the sum of the log props of the each of the token, and then we divided by n. And this was the GRPO objective that we discussed above, and this has some problems. Now let's discuss that. So we took the sum of log props divided by n. Let's say we have two sequences with the same number of sum for the log props, but one sequence is much longer than the other sequence. So as m is longer than the other, so this C1, 1 term would be smaller, uh, because the aggregated log props are going to decrease because of the increasing rollout length. And we have seen that increasing rollout length helps in reasoning. We need more reasoning tokens so that the model can reason about the problem, understand the problem better. So we should encourage having longer rollouts. But this normalization is kind of discouraging this rollout, and and also, like, if your response is way too long and it is bad, it will penalize it less because you're normalizing by the length of the number of tokens. And also it will encourage the correct and short responses. But as I said, we should incentivize the model to increase the rollout length. So this normalization is not good, and as we need longer responses, we need to fix normalizing by the length of the completion here. So in the Dr. GRPO paper, instead of dividing by the length of the rollout, they would have a total max length, or the total length they have provided, like for which they are going to calculate the gradients, and they would divide by that total max length. And this is generally higher for many of the rollouts. However, in DAPO paper, they take out this normalization out from here in calculating this C11. Again, this C11 goes into this calculating the log probes, normalizing the log probes, and getting multiplied with the advantage. So instead of taking the um, normalizing the sum of the log probes in DAPO, if you see here, there is no normalization here. They would take it to the end of while calculating the loss. So if I go back to our diagram here, you had two prompts and you have two completions per prompt. If you see, the first completion was length n, then m, then m, and then p. So DAPO is basically combining those, like the first completions had um, the first completion had length of n, the second completion had length of m, the first completion in the second group had length of k, and the second completion in the second rollout has length of p. So they would take out the normalization out of the log probes, and they would normalize this quantity, the sum of this quantity, and this is the number of groups. So this is how the DAPO loss varies as compared to GRPO, where in GRPO we normalize these quantities, but in DAPO we are normalizing by the total length of the rollouts for the entire group. So DAPO normalization helps with stability, and also we are taking the normalization to the batch level, and you don't have these problems that we discussed about penalizing bad and long responses less and encouraging correct and short responses. And in the paper they saw that after this change, like the reasoning token started to increase. And another adjacent problems of taking the sum of the log probes is, let's say you have the first token with likelihood of 2.0, and the second token which is less likely, the sum of with likelihood of 0.5. So when you are taking sum, it is around 2.5. And also mind that these are just made up numbers. I'm just like getting my point across. But if you take the multiplication, if you take 2 into 0.5, and you get the value to be 1.0. So even if this second token was less likely and the first token was more likely, so this aggregation, this sum aggregation doesn't reflect that, because it is like a increasing value. But if you see this, if you calculate the likelihood of this sentence, if this sequence, you have 2 and you multiply it with 0.5, you get 1.0. So the overall likelihood of the sentence of the sequence decreased. So instead of taking sum, it's a better way to take the multiplication of the log probes instead. And this is what discussed in the paper GSPO, or Group Sequence Policy Optimization. They kept all the configuration as GRPO, same, but instead of taking sum of the log probes, they would just multiply them, and that would be the overall likelihood of the sequence. Okay, now let's discuss about the next ingredient in the GRPO objective, called as the policy ratio or impedance sampling. So going back to our traditional RL setup, you have an agent which takes an action, goes to environment, gives a state and reward. So we have to keep two kind of models. One is the generation model, which is generating these trajectories, and one is the trainer model or current policy model, which is updating these gradients. And at every case steps, we would take our weights and sync with the generation model. We don't want to do this step many times because it has a lot of computational overhead. We would like to do it every case steps. So this generation old policy can be off policy or can be stale, and we need to update it in every case steps so that we can keep on generating with the new policy. And to mitigate this off policiness or stale policy, we use a concept called as impedance sampling. So let's say you have your old props. By old props, I mean the generation policy, like this model, and these are the how much likelihood did the model assign to these tokens. And current props is your trainer model, or the policy that you are trying to optimize, and you would basically take a division or the ratio of each of these tokens, and you will get a R, or the importance sampling ratio, or the policy ratio that we saw in DeepSeek here. So, and the characteristic of this is, if the policy is likely under the current policy, then we should upsample them, and if it is unlikely in the current policy, then we should downsample them. And these are all based on how much reward they are giving us. And uh, and yeah, if your current policy and the old policy is providing the same value, then yeah, like that policy is not likely or less likely. So we update our so this is just another version, like where we had division. If you take the log of that, and you have subtraction here. And so when you are weighting your importance sampling ratio by the reward or the advantage, now you need to decide how much to update each of those tokens in your batch based on your generation policy. And that you determine based on how much reward did your sequence give, uh, which has that token. So we generally update our gradients in a trust region, or in PPO also we have seen this, like we cap our gradients by 1 plus epsilon or 1 minus epsilon. Hence, you in this reward ratio, you see this importance sampling ratio is capped here. So we want to update uh, our likelihood for good tokens, but we don't want to go overboard with it. So hence we will cap it with 1 plus epsilon. And also we want to downgrade the likelihood of the bad tokens, but we don't want to overdo it. Hence we have a clipping here. So this clipping is kind of signaling of uh, and correcting for the fact that you have a generation policy which is generating the trajectories, and you have a current policy which is responsible for getting the gradients based on the advantages and updating itself, and then syncing with the generation policy. So so when you are updating, you have to remain in this trust region, and this has led to stable gradients and stable training for longer run. And you should always pick methods that makes your training run stable. And some of the issues that people have seen with this clipping is in DAPO and in the CISPO paper. This CISPO is by Minimax team, and I have grabbed a paragraph from the DAPO paper. So if you see here, uh, one of the tokens had probability of 0.01, and another token had probability of 0.9. So if you found that in your current policy that these tokens are actually good, and I need to increase their likelihood, but you will be capped to 1 plus epsilon. So hence, if your epsilon is 0.2, so 1 plus 0.2, which is 1.2, and if you multiply it by 0.9, you will get 1.08. Similarly, if when your epsilon is 0.2, 1 plus 0.2, which is 1.2, if you multiply by 0.01, your new updated log props are this 0.012. So if you see your less likely token in your old policy or the generation policy was 0.01, and because of this capping it only went up to 0.012, but this high probability token had a big jump in its likelihood. So so some of the low probability tokens are subdued or do not grow faster in their gradients. Hence, in the paper, they suggest to have this higher clipping to be higher than the lower clipping. So if we go back here, this epsilon and this epsilon are same which is generally taken as 0.2 in GRPO, but in the DAPO paper, they would take this to 0.28 and this was 0.2 as per the paper. And so they are clipping it higher so that these low probability tokens can get higher likelihood under the increased probabilities or the current policy. And if we discuss about CISPO, they don't even clip in the lower half, they only clip in the higher. And yeah, as I said here, like clipping is really high, it's like 5.0. So this is generally done because uh, DeepSeek had a aha moment where they would see tokens like, but wait, okay, wait, I see, there is the problem. So these tokens were low probable initially, but if we clip them, if we don't use this higher clipping, then those tokens would never get higher probability. So we need to use higher clipping, like on the upper range, so that we can increase the probability of these low probability tokens. And another thing to notice in the CISPO paper from Minimax is like the detach. Like in GRPO, we take this mean of RT theta, which is the importance sampling ratio, multiply the advantage, and then we take it to for gradient calculation. But here they detach it, and they're just keep, this doesn't affect your gradients. These are only for importance sampling and clipping, so that higher, so that your low probability tokens increase in likelihood in your update. So CISPO mirrors reinforce a lot, because this is the part for reinforce, and it has just this extra term of having the importance sampling and clipping it higher. So the last ingredient in GRPO is KL divergence, which we see here. And there is this term, this pi theta is the current policy that we saw here. This is the pi theta. And we see another term called as pi ref, or reference policy. We have seen this in RLHF, where the flow works as follow. You pre-train on a big set of data, and then you do supervised fine-tuning, and then you do RL from your human feedback. Generally, this supervised fine-tuning model has good structure. By structure, I mean it follows instructions well, it has good formatting, and then in RL, we get human feedback and change the responses. But we add this scale divergence to our policy so that we do not stray away too much from the reference policy or the SFT policy. And this scale divergence, when you add this scale divergence, so the loss is incentivized to stay as close as possible to your reference policy, and then doing your updates. So scale divergence is basically an incentivization to incentive to stay close to your reference policy. So the Kale regulation that I would really suggest you to look at this John Schulman blog about Kale regularization. So in the John Schulman blog, there are three flavors of Kale regulation. One is minus log delta x, one is this one, and the other one is of this form. And this delta is pi ref by pi theta y given x. And so as per John Schulman blog, this is the most unbiased estimator, and we need an unbiased estimator, so hence DeepSeek went with this estimator for their regularization with their reference policy. But in subsequent papers, like as I said here, K3 estimator, subsequent papers, like if you read the Composer 2 from Cursor, they have this paragraph where they say that the K3 estimator is an unbiased estimator of KL and reduces variance when P and Q are close. However, the variance increases drastically as P and Q diverge. In the chart, also you can see the K3 estimator diverges. So they just use K1 estimator for controlling the regularization. And there are also other papers that came into consensus that K1 as so if you look at K1, uh, when you take the differentiation with respect to theta, this pi ref 10 vanishes. So if you take the log of this, so this will be subtraction, log this minus log 1, and log this one. So if you take a differentiation with respect to theta, this pi ref 10 vanishes. So in your loss, now you, when you're calculating the gradients, you take the differentiation and the pi ref vanishes. So in your loss, the pi ref is not present. So people, so researchers generally suggest to have K2, which is this one, and here the pi ref doesn't vanish to as a loss, and K1 as a value estimator, because this doesn't have the problem that K3 has, where if the P and Q stray away too much. And this is kind of important because as you are training with your RL, you don't want your model to stay close to your SFT data point, because you have gone through a lot of training through human feedback. You would like to get away from this regularization. And many of the papers like DAPO uh, and GRPO, Dr. GRPO, remove this scale divergence because they want the model to stray away from the reference policy or the policy that they started training on. And but if you are using scale divergence, use the K1 as your regularization and K2 as a loss. So this brings us into our presentation. Thank you.